Jai Hind everyone, I am Navjyoti Sharma, once again in front of you to have a lecture on the topic analysis of single phase AC circuits, which is one of the very important topic in unit 2 of the unit steady state analysis of AC circuits of the course BEE 101 or 201, which is fundamentals of electrical engineering according to AKTU. Okay, moving on to the analysis of single phase AC circuits, the contents would be, first of all, the AC circuit containing resistance only, then a purely inductive circuit having only the inductance, and then a purely capacitive circuit having only the capacitance, and then the series combination of either RL or RC or RLC series, and also the parallel AC circuits. Okay, moving on with the very first one, which is a purely resistive circuit. That means how the circuit will behave if a pure resistive load is being attached to a purely sinusoidal waveform, or I must say the supply is purely sinusoidal. If that is so, if at all I say the supply being given to the pure resistor, the voltage is V is equals to Vm sin omega t. I suppose everybody knows this is the instantaneous expression for representing any sinusoidal waveform, right? So, the instantaneous voltage is given by Vm sin omega t. The resistances are, obviously, there will be a voltage drop across the resistor, which we are naming it as VR. The current which will be flowing is I. But how this I will behave, right? Whether it will be in phase with voltage, whether it will be leading or lagging, that we want to know, right? For that, if at all I just see, according to the Ohm's law, I know current must be equals to V upon R. So, obviously, instantaneous current must be equals to instantaneous voltage upon resistance. Substituting for V as Vm sin omega t divided by R, I will be having the expression for the current. Vm upon R will give me what? Vm upon R will give me the maximum current Im, right? So, the expression becomes I is equals to Im sin omega t. So, we have started with V is equals to Vm sin omega t, and we got the expression of the current as Im sin omega t. What does this signify? It signifies that voltage and current, what is the phase of the voltage over here? The phase is 0. Similarly, what is the phase of the current over here? That is also 0. That means both of these are in the same phase. The voltage and current will be in same phase, right? In the phasor diagram, I may represent them like this. VR and the current is also in the same phase. That is for purely resistive circuit. If that is so, what is the power factor for a purely resistive circuit? Power factor, that is cos of the angle between voltage and current, right? The angle between voltage and current, that is 0. So, cos phi, that becomes unity. That means for a purely resistive circuit, the power factor of the circuit has to be unity always. Okay, how to have the power? Now, if at all you see in any circuit, the electric power consumed at any instant, right, that is nothing but the product of the voltage and current at that particular instant, right. If you just see here with a phasor diagram, if at all I explain it, this is the current waveform. Right, generally the magnitude of the current is generally in the circuits we used to have it smaller, and the voltage is having higher magnitude, but both of them are in same phase. They are initiating at same point, they are attaining their maximum at same point, they are once again attaining their minimum at the same point, negative maximum at the same point. That means both of them are in the same phase. But what about the power? If at all I see, if at all I plot the power according to V and I both are positive from 0 to pi. So, obviously, the power will also be V multiplied by I, and that too positive. Once again, in the negative half, if you just see voltage and current both are negative, negative makes it positive. So, the power will once again be positive, right. If that is so, what will be the expression for the power, right. So, let us start with the instantaneous power. The instantaneous power can be given by instantaneous voltage multiplied by instantaneous current. What is instantaneous voltage? Vm sin omega t. What is instantaneous current? Im sin omega t. Both are in the same phase. If that is so, I am getting Vm Im sin square omega t. If that is so, sine square omega t can be replaced by 1 minus cos 2 omega t upon 2. So I'll be having two components, Vm by 2 and Vm by 2 cos 2 omega t. But this is, once again, this is the instantaneous power, right? But what we want to have? We want to have the average power. Okay. For an average power, this is a constant value. Fine, we can be looking it after, right? We know for finding the average over a curve, we need to have area under the curve divided by length of the base of the curve, right? The base of the curve, if at all we see, the base of the curve is 2 pi. So I am making it at 1 upon 2 pi, integration 0 to 2 pi, Vm Im by 2 d omega t, and once again Vm Im by 2 cos 2 omega t d omega t, the two components, right? Once again, if at all I integrate it over a complete cycle, this is cos 2 omega t. So this component is going to get 0, right? So this component is getting 0, but here if at all I do, it will be Vm Im by 2 only. Once again, this 2, I can be writing it as Vm by root 2, Im by root 2. Vm by root 2 gives me the RMS value of the voltage. Similarly, Im by root 2 gives me the RMS value of the current, which makes that the power, the average power consumed by a purely resistive circuit is given by V into I, where V and I are the RMS value of the voltage and current. Similarly, now it is a purely inductive circuit now. How the circuit will behave or how the current will behave if at all this sinusoidal supply being given to this inductor, right? In case of inductor, we know once this inductor, it opposes the sudden change in the current, right? So obviously, when this alternating supply is being given to the inductor, there will be an induced EMF in it, right? This induced EMF, if at all you just see, that induced EMF is equals to minus L di by dt, where what is this L? Inductance, rate of change of current. But once again, because of the Lenz's law, this induced EMF will also oppose the very cause producing it. And what is the very cause producing this induced EMF? The supply voltage. So this E will also oppose this supply voltage, right? So I may be saying V must be equals to L di by dt, right? From here, I may be finding the expression for I by integrating it, right? If at all I do this, I will be getting an expression Im sine omega t minus pi by 2. But what will be the expression of this Im? How do I get this Im? This Im must be equals to the maximum voltage upon omega L. What is this voltage? This voltage is Vm sine omega t is equals to L di by dt. Go for the integration. For finding this I must be equals to Vm by L integration sine omega t dt. When I do this expression, this omega will come over here, Vm by omega L. Vm by omega L gives me XL. What is XL? This is the inductive reactance of the inductor, XL, right? So Vm by omega L, which is given by XL, omega L is given by XL, 2 pi FL, the inductive reactance. Vm by omega L will give me the maximum current Im sine omega t minus pi by 2. So from these two expressions, what I am getting? This is the expression for voltage. What is the phase of the voltage? That is 0. What is the phase of the current? That is minus pi by 2. Am I correct? If that is so, if the phase is minus pi by 2 current and here the phase is 0, if that is the case, I can conclude that in purely inductive, the current used to lag the voltage by 90 degree, and that is what is being shown in case of the phasor diagram. If at all I take current to be as the reference, right, current to be as the reference, in that case, the current should lag the voltage by 90 degree, or I must say the voltage should lead the current by 90 degree. So that is So the voltage is leading by 90 degree or the current is lagging by 90 degree. If that is so, what is the power factor for a purely inductive circuit? Power factor, cos phi, cos of the angle between voltage and current. What is the angle between voltage and current? 90. So cos 90, that makes it 0. But what is the nature of the power factor? Nature of the power factor, whether it is leading, whether it is lagging. And that is decided by whether the current is leading or lagging. So if at all you just see here, what is current doing? The current is lagging the voltage by 90 degree. If that is so, the power factor would be 0 lagging. I'll be mentioning it, 0 lagging, right? Okay, so we are done with the relationship in voltage and current. Now, once again the power. What will be this time the power, average power consumed by a purely inductive circuit? Okay, once again going with the instantaneous power. Instantaneous power given by V into I. Once again, instantaneous voltage, Vm sin omega t. Instantaneous current, Im sin omega t minus pi by 2. Right? So that makes it minus Vm Im sin omega t cos omega t. Substituting for the formulation 2 sin A cos A, that gives me sin 2A. That 2 will come over here. So I'll be having minus Vm Im by 2 sin 2 omega t. Right? Once again, this is only the instantaneous power, but I want to have the average power. Right? Average power, taking the length of the base of the curve as 2 pi and also integrating it up to 2 pi. Vm Im by 2 minus sin omega t d omega t. But I know for a complete cycle, it's a sine wave. Although the frequency is double, sin 2 omega t, we can be seeing it in the graph as well. The frequency is being doubled, but this is a sine wave. Over a complete cycle, the average value is going to get 0. Right? So the average power consumed by a purely inductive circuit is 0. Right? If you just see here, now, this is the waveform representing the voltage. Once again, the current used to lag the voltage by 90 degree. If that is so, the current will start after 90 degree. It doesn't mean the wave is not existing earlier, right? But it is lagging the reference by 90 degree. So the current is starting from here, right? Obviously the magnitude is smaller. But if at all now plot the power in it, if at all I see in this 1/4 of the cycle up to pi by 2, the voltage is positive but the current is negative. If that is so, the power will also be negative, V into I. Any one of the quantity is negative, then the power will be negative. Similarly, for this another 1/4 of the cycle, that is from pi by 2 to another cycle. In this case, if at all I just see here, now the voltage is also positive and the current is also positive, so that the power is also positive. In another 1/4 of the cycle, if at all I see, the voltage is negative and the current is positive, but the voltage is negative, so the power will be negative. Once again, in the last fourth, if you just see here, the voltage as well as, if you just see here, the voltage and current both are negative. The current is also negative and the voltage is also negative. Both are negative means negative makes positive. So the power is also positive. But if you just see, whatever is the positive is negative, I'm getting positive negative halves equal. So over a complete half, they are going to cancel out each other. So the average power is once again going to get 0 for a purely inductive circuit. Coming to purely capacitive circuit. Okay, now this is a purely capacitive circuit. Once again, a pure capacitor is being fed with the sinusoidal supply, V is equals to Vm sin omega t. Now in this case, how the current will behave? I know when you make the sinusoidal supply being applied to the capacitor, on the plates of the capacitor, the charge would be stored, that will be given by Cv, where C is the capacitance and V is the voltage, instantaneous voltage, right, which is given by C Vm sin omega t. But we don't want to have the expression for charge, we want to know how the current will behave, right? But I surely know that the current is given by the rate of change of charge, dq by dt. Just mention that. dq by dt, that is d by dt. Q we have already derived, that is CVM sine omega t, right? Now once again, when I differentiate it, right, CVM is outside, differentiate sine, cos, once again converting that into sine, I'll be having sine omega t plus pi by 2. And what will be the value of this Im? Im is given by Vm upon 1 upon omega c. Here I'll be having omega being multiplied, or I may be taking that towards the numerator and I'll make it as 1 upon omega c. Now what is this 1 upon omega c? A very significant step. That is given by Xc. 1 upon omega c is Xc, that is capacitive reactance. The reactance offered or the resistance offered by the capacitor to the flow of the current is being called as capacitive reactance, and its unit is once again ohms. Likewise resistance, likewise inductive reactance, the same unit is with capacitive reactance having the unit of ohms. Once again, Vm, maximum voltage by this reactance, will give me maximum current sine omega t plus pi by 2. Concluding, what voltage is Vm sine omega t having the phase of 0? Im sine omega t plus pi by 2 having the phase of plus pi by 2. So obviously, the current will lead the voltage by 90 degree. That can be seen from our phasor diagram. If at all I take Vc as my reference voltage, if that is so, here the current is leading the voltage by 90 degree. Once again, what is the power factor in this case? The power factor cos phi, that is given by cos of the angle between voltage and current. Once again, the angle between voltage and current is 90, as that in case of purely inductive, right? This is also 90. So that makes me 0. The power factor is once again 0, but what will be the nature here? Is it once again lagging as in case of inductive? No. If at all you just see here, the current is leading the voltage. If current is leading the voltage, the power factor will also be leading. The nature of the power factor, that is decided by whether the current is leading or whether the current is lagging. So the power factor is 0 leading. Once again, instantaneous power, or for which I want to know what will be the average power. If at all I see, once again it's the same expression more or less. Am I correct? It is once again instantaneous voltage, instantaneous current, Vm sin omega t, Im sin omega t plus pi by 2, omega t plus pi by 2, I may substitute it as cos omega t, right? So the power expression is Vm Im by 2 sin 2 omega t. This is instantaneous power. But when I am going with the average power, I'll integrate it up to 0 to 2 pi with the time period of 2 pi. If that is so, once again the average value over a complete cycle is going to get 0. So there is no average power consumed by a purely capacitive circuit as well, right? So the power absorbed by a purely inductive circuit is 0. The power consumed by purely capacitive circuit is also 0. Okay. The same thing can be seen in case of the graph as well as what we have seen in case of inductive, purely inductive. Here, if at all I see, this is reference, the voltage starting with 0 and ending with 2 pi. If at all I see with the current is leading the voltage by 90 degree. That means it must have started somewhere here, and this is supposed to be pi by 2. This angle is supposed to be pi by 2. That is so here, right? In the very 1/4 of the cycle, if at all I see, both the voltage and current are in positive, so the power is also positive. The voltage and current here, the voltage is positive but the current is negative, so it is negative. Same way, positive and negative. But over a complete cycle, all the positive halves will be cancelled by the negative halves. So the average power is going to get 0. Now, an RL series circuit, if at all I go with an RL series circuit, now we have seen the purely resistive, inductive and capacitive values. Now, if at all it's an RL series circuit and that is being supplied within sinusoidal voltage of V. Once again, this is the instantaneous voltage. V is given by some Vm sin omega t. V is given by some Vm sin omega t. So how the circuit will behave this time, right? Is it going to get us a leading power factor or lagging power factor, whether it will lead by 90 degree or lag by 90 degree, right? So that can be easily done with the help of the phasor diagram. If at all you just see. Here, I know it's a series circuit, so the current which is flowing is going to remain same in both R and L, right? But the voltages are going to get divided. The voltage across the resistance would be VR and the voltage across the inductor is, say, VL. We are naming it, right? If that is so, can we have the phasor diagram being drawn for a purely resistive and inductive, for VR, VL, plotting V and I? What should be our reference phasor? The quantity which is same to all, right? If that is so, the quantity which is same to all is current. So I'll take the current to be as our reference phasor, right? Where should I plot VR? What is VR? That is purely resistive voltage, the voltage across a pure resistor. If that is so, what should be its nature? We have just studied for a purely resistive circuit, the voltage across the resistance and the current must be in same phase. So VR and I will be in same phase. Whereas, what about VL? VL will lead, or I must say the current will lag the voltage by 90 degree, or the voltage will lead the current by 90 degree. So I am making it leading. If that is so, the resultant is over here. So V is given by the phasor addition of VR and VL. This is the supply voltage, this is the supply current. The angle between voltage and current is given by our power factor angle or phase angle phi, right? So if at all I say V, we have already written here, this is my resultant V, and V is given as Vm sin omega t. If V is given as Vm sin omega t, I can give the current as, the current is now lagging the voltage by an angle phi. If that is so, I'll say I is equals to Im sin omega t minus phi. That means the current is lagging the voltage as in case of purely inductive, but not by 90 degree, by a certain angle phi, which can be given, right? Which can be given as tan inverse VL upon VR, right? If that is so, now coming to the three powers. In case of purely resistive, inductive, capacitive RL circuits, we can be having the three kinds of powers, right? What are the three kinds of power? It can be apparent, true and reactive powers. Especially in case of RL, right? In case of, we have seen, in case of purely resistive, we are only having the average power, which is also being called as true power, right? In case of inductor and capacitor, we can be having the apparent power. Okay. So what is this apparent power? The apparent power, the total power that appears to be transferred between the source and the load is called apparent power, and it is equal to the product of the applied voltage and the circuit current. That is, it is just given by the voltage multiplication of V into I and denoted by the letter S. It is measured in volt ampere. Whereas what is true power? That is also named as active power, true power, real power taken by the circuit, or the average power absorbed by the circuit. So the power which is actually consumed in the circuit is called true power. It is measured in watts, given by VI cos phi. V and I are the RMS value of the voltage and current. Cos phi is the power factor of the circuit decided by the kind of load we are connecting. And lastly, the reactive power, the component of the apparent power which is actually neither consumed nor does any useful work in the circuit, that is being called as reactive power. It is measured in VAR, volt ampere reactive, and is given denoted by the letter Q, VI sin phi. The further lecture, which includes the RC circuit, RLC series and the parallel circuit, that can be taken on in the next lecture. Thank you very much.